Now in example 1, it is just a number, so it's simple enough to simply say simple, simple, simple. Okay. Okay. As we have said, m minus 9. If I keep saying n, I mean 9. m minus 9. Max quality. Let's look at the 11-6 lesson, rational expressions with like denominators. So as we've been doing throughout this chapter, rational expressions behave much like fractions. And so as we transition from multiplication and division into addition and subtraction, one thing you should be watching out for are common denominators, right? We cannot add or subtract fractions without common denominators. Now, lesson 11-6 is all about rational expressions that already have like denominators, with one small exception at the very end in example 5. But with these other examples, like say example 1, which I'm writing down right now, 3n over 12 plus 7n over 12, since both of these are already denominated in twelfths, right? Like imagine we had 3n slices of pizza out of 12 and 7n slices of pizza out of 12 in another box. If we were to add these together, what would we have? Well, hopefully your numerator for sure you recognize, oh, we would have 10n slices of pizza. But what would our denominator be? And again, let's use some actual numbers real quick. Let's actually say it was like 3 out of 8 slices of pizza plus 7 out of 8 slices of pizza. As we put these into a new box, so there's 3 out of 8, right? 1, 2, 3 of them, and then 7 out of 8. How many total slices do we have, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Unsurprisingly, 10 is our numerator. But what's the size of the slices? When we put them into a new box, do they get smaller? Do they become only a 16th of the pizza? No, of course not. They're denominated in eighths. The size of the slices stays the same. That's what the denominator is telling us, the size of the slices, even when it's an expression, a variable expression, rather than just a number. Now in example 1, it is just a number, so it's simple enough to simply say 10n divided by 12, 10n over 12. We do, of course, want to factor anything that we can or cancel anything that we can, so I notice 10 and 12 are both multiples of 2, and so this ends up being 5n over 6 as a simplified sum, the result of addition there. I'd like you to try the same thing, add your numerators, keep your denominators the same, on Check Your Progress 1A and 1B. All right, there you have my answers for Check Your Progress 1A and 1B. On 1A, I add my numerators. 8x plus 5x is 13x. My denominator stays 6. Again, we're not changing the sizes of the slices of pizza. Check Your Progress 1B. Now, denominator, simple enough, stays 5dy. Numerator, do 4x and 7 add together? Yes, they do. But they don't simplify as they do so. They don't become 11x, or just 11, or 3, or 28, or I don't know, anything else you would think of, because they're not like terms. When we write their sum, we just write 4x plus 7. So that's what you can see I have there in my numerator. 4x plus 7. Let's go ahead and jump into example 2. This does not only work for monomial-like denominators, any like denominators will do. So let's say I have 2x over x plus 1, and I want to add to that 2 over x plus 1. Now the first thing I do is, again, add my numerators. They are not like terms, so it just becomes 2x plus 2. And the denominator does not change size. It stays x plus 1. However, in this case, I'm not done because I should notice, wait a second, 2x and 2, although they were not like terms, do have a common factor. And so I can factor that out via the distributive property to say, oh, that's the same as 2 times the quantity, x plus 1. And then once I do that, hopefully you notice, oh, those cancel. Just like over here, where we canceled a 2 out of the 10 and the 12 because it had the 2 in common, we can cancel binomial factors as long as they are in common between numerator and denominator. That's why we would say this expression simplifies down to 2. Now, is it always 2? Does this expression always evaluate to 2? I mean, imagine that we said, let x equal 10. This would be 20 over 11 plus 2 over 11, which is, in fact, 2. Maybe let x equal negative 27. I don't know, right? This would be negative 54 over negative 26 plus 2 over negative 26, which would be negative 52 over negative 26, which is still positive 2. Okay, I feel pretty good. It looks like it is simplifying to 2 no matter what. Can you think of the one number that won't be true for? Jeopardy music, anyone? Let x equal negative 1. What's the big deal, you say? Doesn't it just work out the same way? No. What on earth is going on here? We get negative 2 over 0, which has no meaning, plus 2 over 0. Is that 0 over 0? I don't even know. Either way, when I see those denominators of 0, that makes the expression undefined. And so it's not that I can go back to 2 or that it fails. Well, I mean, I guess it does fail in some sense to go back to 2. But the reason, basically 2 is not the problem. It was that negative 1 we were plugging in, which of course you should recognize, oh, that was the excluded value. And so that's why it didn't work. All right, take a moment and work out, check your progress, 2A and 2B. There is my work and my 2 answers for check your progress 2A and 2B. 2A works out simply to y. B works out to 5x plus 1 over 11x plus 3. You can see adding numerators, factoring things out, and canceling. That's how I got those answers in each case. Let's jump ahead to example 3. Find the expression for the perimeter of parallelogram PQRS. No. We're just going to skip that. Let's jump into example 4. So on example 4, we're doing some subtraction instead. We've got 3x plus 4 over x minus 2 minus x minus 1 over x minus 2. Now, first of all, with subtraction, we still need common denominators, which fortunately we have here, right? X minus 2, x minus 2. We still have our common denominators, but we have to be really careful here. We are subtracting a whole expression, and so I usually represent that with parentheses. That reminds me to subtract everything. So the 3x minus the x leaves 2x, and the 4 minus negative 1 actually becomes positive 5. X minus 2, of course, is my denominator. Nothing factors there, therefore nothing cancels, and that's that. That's my final expression, 2x plus 5 over x minus 2. On example 4b, we have 3m minus 5 divided by m plus 4, and we are subtracting 4m plus 2 divided by m plus 4. So first things first, again, I am subtracting. I want to remember to subtract everything. So that gives me negative m. 3m minus 4m is negative m minus 7 divided by m plus 4. If need be, I could factor a negative 1 out of that numerator because I noticed both of the terms were negative, but it wouldn't materially change anything. Nothing cancels, no common factors, and so that's that. Take a moment and work out Check Your Progress 4a and 4b on your own. Okay, there are my answers for Check Your Progress 4a and 4b. For 4a, we've got h minus 1 over h plus 1. For b, we've got 3h plus 2 over 3h minus 1. So, a little factoring and canceling there on 4b, but the main thing is just getting the subtraction right. Let's finish up with example 5. I mentioned earlier this one, there was something that was a little bit strange, but hopefully not too terribly strange. So let's take 2m over m minus n, and let's say we want to add 4m over, m minus 9, and then the second one 4m over 9 minus m. Are these like denominators? If this was, say, m plus 9 and 9 plus m, we would say for sure, because addition is commutative, right? The order makes no difference. However, with subtraction, that's not really true. 10 minus 2 is 8, but 2 minus 10 is negative 8, which although they are obviously related to each other, are not the same number. But let's go to that obviously related to each other part. 7 minus 4 is 3. 4 minus 7 is negative 3. 100 minus 40 is 60. 40 minus 100 is negative 60. When we flip subtraction, although it's not the same because subtraction is not commutative, they are additive inverses of each other. In other words, whatever m minus 9 is, if we called it a, 9 minus m would simply be negative a. It would just be the negative of whatever the first one was, right? So we can use that to our advantage if we do something like the following. Let's go ahead and change this. The 2m over m minus 9 we'll leave alone, but the 9 minus m we're going to represent as that additive inverse. It must be the negative of whatever m minus 9 is. But then that negative, because that's essentially like a negative 1, right? We can actually divide the 4m by the negative 1. It just turns it into a negative 4m. So this becomes 2m over m minus n plus negative 4m over m minus 9. If I keep saying n, I mean 9, m minus 9. Using the additive inverse, we have created like denominators where they did not exist a moment ago. This will be really important in the next lesson. And of course, you know it's important for adding and subtracting fractions in general. We don't often have common denominators. We often need to make them ourselves. In this case, though, once we do our subtraction, 2m minus 4m is negative 2m. And of course, our denominator, now that it's a like denominator, is just m minus 9. That is what example 5 ends up looking like. I'm not going to have you do the check your progress because I know this is a little strange, but let me walk through a and b with you really quick. So 3n over n minus 4 plus 6n over 4 minus n. Again, anytime I see something like 4 minus n, which is the flip of n minus 4, it's not the same thing because subtraction is not commutative, but it is an additive inverse. And so it's the same thing as negative 1 times n minus 4. If you distribute the negative 1 right now, you might see why that ends up working the same way. You are going to have a negative n and a positive 4, which is the same as 4 minus n. So hopefully you can see, essentially we're factoring out a negative 1 when we do this. And then usually, we could turn it into subtraction. We could send it up to the top. It doesn't really matter. Let's say I turn this one into subtraction. 3n over n minus 4 minus 6n over n minus 4. Either way, we're going to end up with negative 3n over n minus 4. And so that's Check Your Progress 5a. If you want, you can tackle Check Your Progress 5b on your own. You can just pause the video here. But again, I am going to just go ahead and talk through it. We've got t squared over t minus 3 plus 3 over 3 minus t. I'm going to change that t minus 3 into a negative 1 times, that 3 minus t, I'm going to change into negative 1 times t minus 3. And so really that negative 1 we can just send right up to the top. Those are the same expressions. This and this are equivalent. And so then we get t squared minus 3 as our new numerator over t minus 3. Much as it looks like these would cancel out, maybe it leaves something like t. No. There's no factoring we can do here, at least not with integers. And the minus signs mean that we can't just randomly cancel things out that look like they should cancel out. So that is that for Check Your Progress 5b. I hope that was helpful to you. Adding and subtracting rational expressions with like denominators, we can treat much like we treat adding and subtracting fractions with like denominators. We add or subtract numerators, and then we leave the denominators alone. They simply tell us the size of the fractions. They do not actually get added or subtracted together. If we have something weird, like denominators that look the same, but perhaps are slightly different because subtraction is not commutative, we use additive inverses to make them like denominators. That concept of making like denominators will be very important in the next lesson. As always, if you have questions, please feel free to comment down below. Or actually, I think it's impossible to comment. I learned today, so I don't know why I've been saying that the whole time. But I guess instead of commenting, you can email me, you can text me, you can like and unlike the video over and over again so I get notifications. No, don't do that. That sounds terrible. Find a way to let me know. I hope it makes sense, but if not, I want to help you out. You guys have a good night, day, whatever.